on the YouTube channel, and I'll give you a link to the live versions of all these lectures as well. So you'll be able to see that on my courses. Hopefully sometime today. We'll see how friendly the video creation software is with me today. So thank you for coming. I know it's all a little bit weird, right? Taking classes in the summer is not maybe something we typically do, but I'm glad we have the opportunity to do this, especially in kind of a small class, because this class, there's sort of two camps in mechanical engineering, right? I think that, related to thermodynamics, it's kind of a polarizing class. I think people like me love it and say like, oh, it's the best class, it's my favorite class in all of mechanical engineering. And then a lot of people hate it too. Because I think it's because it's, it can seem like some of these ideas are pretty big, right? And sometimes conceptual. And a lot of times I think people go into mechanical engineering because we like problems that we can picture, right? Like if I have a pendulum and I pull it back and I let it go, I can picture in my head what's supposed to happen. Right? Now that's maybe different than something like electrical engineering, where I don't have the mental picture necessarily to think about what those electrons look like as they're flowing through a wire. And some of thermo starts to be like that, especially as we start to talk about entropy and things. Right? But we're going to start in thermodynamics by talking about conservation of energy, right? Which is sort of the core principle of thermodynamics. It's called the First Law of Thermodynamics, is this idea that energy in the universe is conserved, right? But before we get to that, I'll give you a little bit of introduction, talk a little bit about myself, and then sort of give you a bit of a background on the course and how your grade will be calculated. Right, so this is a picture of me, at least me when I was hired, right? So that's maybe 8 years ago now. Our class, despite the fact that the Zoom link says it starts at 10 o'clock and not 10:10, the class will begin at 10:10, but I couldn't get it to put a meeting to start at 10:10 because Zoom thinks that this is kind of a weird start time, right? Office hours, I've put up a link and I'll show it later, but there's a link in the announcements for a survey where you can just kind of color in where your availability is, and I can pick an office hour time that works for all of us, especially since it's kind of a small group. I'm hoping that won't be too difficult to do. So a little bit about myself. I grew up across the lake from Rochester, just outside of Toronto. So I grew up in Canada. I moved here in 2013 to take this job at RIT. This is a picture of my three girls. So at home, three girls at 11, 9, and 3. So pretty big handful, especially doing school from home these days, right? So things we like to do, we like to play board games, right? This is a game called Stuffed Fables, which is kind of like a really watered down sort of Dungeons and Dragons where the board is the dungeon master. Maybe if anybody's played Gloomhaven, which we also play, is kind of like a watered down version of that too, in more of a kid-friendly theme. This is also a pretty fun game. I don't know if you played the Funko Pop games, but there's kind of a reasonable amount of strategy in here, and the girls are madly in love with Harry Potter, so we like to play this one too. Another thing that I like to tell all my classes, because this is something I got into, I don't know, maybe 3 or 4 years ago, but you all have access. There's an app called Overdrive, or it's I guess sister app called Libby, which gives you access to public libraries that you have memberships to. And at first I thought, well, that doesn't really matter too much because like the Monroe Public Library here in Rochester, I mean, it's not bad, but it doesn't have a huge selection. But if you have a New York mailing address, right, which I assume most of us do, at least during the school year, then you also have free access to the New York Public Library, which has a huge collection of audiobooks. So if you're interested in listening to audiobooks, if you're working out or going for a walk or something, I suggest downloading Overdrive or Libby, and I think you have to send them maybe a picture of a piece of mail or your driver's license or something to get access to the New York Public Library. So that's something, I'm all about the free stuff, right? So I try to be financially responsible, and I think audiobooks, when they're free, are awesome, right? So my background, when I went to school at a place called McMaster University, which is in Hamilton, Ontario, so just west of Toronto, sort of like kind of like the Pittsburgh of Canada. Used to be a big steel city, now transitioning more to education and healthcare. I did a double major there in engineering and business. This is where I met my wife, and she took a different path, right? So after that, we had the option to do an MBA in 1 year. So that's what my wife did. I went on to do a master's degree and a PhD, so I ended up here. Now, we didn't have co-op when I was an undergrad, but I did have the opportunity through some networking that I'd done to work at what was Daimler Chrysler then, because they were owned by Daimler, making big full-size vans in Windsor, which is across the river from Detroit. So I have a lot of family there in the automotive sort of industry, and they helped me kind of get a job over there. So I did that for 2 summers. Figured that even though I enjoyed that industrial setting, I didn't really want to spend my life in that atmosphere. It was too much. I felt just trying to keep the line running for the next 20 seconds, right, or the next 30 seconds, because there's so much money involved when the line goes down. So after that, I did a couple summers as an undergraduate research assistant, and then sort of kind of fell in love with doing research, right? So my first research project as a master's student was looking at how do we cool electronics in space. So electronics sort of give off a lot of heat, right? Particularly high-powered electronics. And you might think that in space that should be pretty easy because space is pretty cold, right? But it's actually because we generate heat in such small areas that the heat flux or the heat per unit area is really high. So we still need a way to sort of get that heat out into the environment. So we were looking at different ways to do that using capillary forces. One of the ways you do this here on Earth, right, is that you just have whatever your heat source is low, right, and then it would boil some water, right, and that vapor would move up, right? But the reason that the vapor moves up, or really that gravity pulls the liquid down, right, is because of gravity, which doesn't work in space, right? So we were trying to think, how could we run a similar kind of heat transfer loop that's multi-phase, that's boiling fluid in space, right? So this was a pretty cool project. Then in my PhD, and what I mostly do now is this idea of digital microfluidics. So here we take small droplets, maybe 100 nanoliters of fluid. These are on checks that are maybe 1 millimeter by 1 millimeter. And that fluid is sandwiched between 2 plates, kind of like the white part of an Oreo cookie here. And those plates are separated by about the thickness of your hair. So about 100 micrometers, so 1/10 of 1 millimeter. Right? So we're trying to do that to automate biological protocols to try to make things more accessible, right? So, or maybe like, we all do these coronavirus tests where they stick something up our nose, right? And then they, they clip that, they send it off to some medical diagnostic lab, and in a couple of days you get a result back. But with devices like these, the idea is maybe we could do these kind of tests on site so we wouldn't have to use sort of traditional medical diagnostics, right? This is also pretty cool, right? So here I like this picture. Here we've got this droplet. We slowed this down a lot because these water droplets are almost like water balloons, right? They have this almost like elastic skin around them. That's where the air meets the water, where that interface is, right? This is why I don't know if you've ever seen bugs walk across water, right? So that's kind of like me and you walking on a trampoline, right? Because that skin where the water meets the air is kind of elastic, right? So here, if you understand the elastic properties of that and a little bit about mechanical engineering, we can make these droplets jump up and down, right? They jiggle a little bit like Jello or something, right? I just like showing that video because I think it's cool, right? Now, usually these kind of devices, I don't know if here at RIT you've walked by the clean room. People got the ninja suits on there in Building 17. Usually you'd make these devices there, but we've kind of made up a way to just inkjet print these things with a printer we bought off Amazon for like $100. So you lose in resolution, but it makes it so people could come in and sort of easily sort of, come in and make progress in the lab. This is some work we've been doing with these sort of lab on a chip type things, trying to assemble different pieces of DNA, right? So we're trying to make long pieces of DNA for things like, genetic protocols to try to, get personalized healthcare. So really what we're doing, and maybe because I'm a mechanical engineer, I think about these little pieces of DNA like Lego bricks, right? And we're putting them together, right? So that's what this gel shows, right? That smaller pieces come further down the gel, right? And bigger pieces don't. So this just shows that we took these two pieces of DNA and we sort of fused them together. Right, so we work in different applications, looking at droplets drying and the patterns that they make, right, to try to make flexible electronics or maybe do blood diagnostics. And then we're trying to get into this sort of personalized healthcare where we take a lab, right, and we shrink it down and automate it onto a microchip. So that's kind of the research that I do. We've had lots of people over the years come in and help us, right? So this is always a bit of a shameless plug. If you're on campus and you're interested in doing research, you can look me up and we can try to spec out a project for you if you're interested. Or if you're interested in other areas, you can talk to me and I can try to point you in the right direction for someone else on the faculty that's interested in the kind of work that you're interested in doing. So the first thing that I want to talk about is the syllabus, right? So how does the class kind of work, right? So how do you get your grade in this class, right? So the reason that I shifted those first 3 lectures to being asynchronous is because I don't just want to read the book to you, and it felt like that's what we were doing in the first couple lectures, right? We're going to try to solve a lot of problems in class. So classes will be sort of divided, and some, not just one class by one class, but sometimes like the first half is instruction and then we'll do problems. So we do try to do a lot of problems in class. So online I've got this, writing tablet, so we'll do this. Or in the problem we do today, I just have animated the solution through in PowerPoint. That's a little faster, and I think we need the speed today, but normally I'll try to go through problems on the drawing tablet so that we can see how to do the problems, right? And I think, this is the first class where I feel like we start to learn how to do what I think of as engineering, where we sort of know what the equations are, but we don't necessarily have all the inputs, right? So we have to use our understanding of the physics to try to figure out which terms in the equation are most important. So we'll cancel out some things that we think are not important, right? Now, when I was an undergrad, I was always looking for a slide like this, right? How does your grade get calculated? And sort of the baseline way your grade will get calculated looks like this. I think this is pretty standard, where we have 10% going to quizzes, 10% to homework, 2 midterm exams, 25% each, and 1 final, which is 30% each. Right now, because I'm kind of more interested in what you know at the end of the class than at the first 2 sort of milestones, we do have these other 2 grading schemes. Basically, if you do better on the final than one of your midterms, what we'll do is we'll drop the lower midterm or the midterm that your final is better than, and we'll add that weight to the final exam. Because the way this class works, it's very cumulative, right? So if you can show me you can do the stuff that we do at the end of a class, like you can analyze how a nuclear power plant works, then I know that to do that you needed to be able to use the same techniques that we were doing on the first and second midterm, right? So we have these different alternate strategies. Now, obviously, because it's an online class, the exams will be done online. I think that we'll do this in the way that we did last fall when I taught this class, where there'll be the different modules of the exam. So typically there'll be a multiple choice part and then long answer parts. And what we'll do is we'll give you a set amount of time to do each of those different parts. They'll all be open book, and then we'll give you a little bit of time in between just to make sure that you can recenter and then start on the next part of the problem. So as we get closer to the first midterm, I'll put up the details of how that exam will be administered. This is what a typical week looks like in thermo, right? So on Mondays, your quiz will be assigned. So there is a quiz assigned already based on the sort of pre-work, right? The 90 minutes of lecture that I've asked you to watch. Those quizzes will be due on Sundays. And then throughout the syllabus, if you look, I don't know if you had a chance to look at the syllabus yet, but it shows that for every lecture there are a certain number of homework problems. So then those homework problems associated with those different lectures will be due on the Monday following that week, right? So there's no homework due obviously this Monday, meaning like whatever it is 2 days ago. But next Monday there will be homework that's associated with the lectures that we do this week. Now, there is a recommended textbook for this class, but I will be posting the like snips of what the homework problems are. So if you can get your hand on an old version of the textbook, right? So I think I brought it home, but I have I used the same textbook when I was an undergrad, but it was like the 3rd edition instead of the 9th edition or something. And the material in there is just as good. It's just the questions are a little different. So I'll post the questions for you, and then we'll also post the solutions to those problems. Right, so the quizzes, we'll take the average. There'll be 10 quizzes. I guess maybe 9, because one of the quizzes right now I have as being open, so maybe I'll just give everybody 10 for that quiz. And then the average of all the homework sets, right? So that's how you'll get to the 10% that's associated with both of those things, right? We'll grade homework in this way. So you'll upload your homework to the Dropbox. The Dropboxes should already be live on my courses. And then I'll look at all the problems. I'll randomly pick one, the same one for everyone in the class, and I'll grade that one a little bit more rigorously, right? But I'm more concerned that you're following the homework process that we lay out, right? And I'm less concerned with you actually having the correct answer, right? So we'll grade that out of 7, right? Did you attempt the problem? Did you follow the right format? Did you make reasonable assumptions? Did you follow the right method, right? I'm less interested in the numerical answer, right? And then basically for all the other problems that are due, I'm just going to have a look and say like, oh, did you do them, right? And that'll be worth 3 out of 10 for a given problem set. We'll also have office hours. I think office hours are a good way. This is, like I said, this is a class that people tend to find to be relatively difficult. So I think trying to stay on top of things and coming to office hours is a good idea. Right? If you got Netflix, this Beatbug show is pretty good. They do like Beatles covers, but weave a story around it. It's fun to watch with my kids anyway. Right? So you can come and we'll do live problems. I have no problem actually even doing the homework problems with you, because I think that that's a good way to learn. Right? Like I said, I think that I'll end up just posting the homework solutions potentially even before the homework is due. But what I really want you to do is focus on what's the method, right? Because that's ultimately what we're trying to teach you is, if you can, the way that I try to teach this class is that there's a very structured method to all of these problems. And if you can follow that method, every problem ends up looking just about the same. And then that takes, because I think the hardest part about any exam, right, is when you first look at the page and you're like, I don't know, like those first couple minutes where you're like, how do I approach this problem, right? So we really sort of use the engineering approach of kind of systematizing these types of problems so that you look at that problem and you say, I'm not really sure what I'm doing here, but I'm just going to trust the process, right? And if you trust the process, you get the ball rolling, right? You start that inertia, and then I think good things will happen, right? So it looks like 3 of us have submitted this when to meet link. So I have this also on the My Courses page. If you go in here and you just, it's a bunch of little cells and you kind of paint when you're available. And then it gives us this color map where the darkest green areas are when most people are available. So since homework is due on Mondays, I'm thinking that this Monday time somewhere in here probably looks good, but I'll wait to see what people's availability looks like. Okay, now we can start to talk about thermodynamics, right? Now this class, it's kind of about the universe, right? And that's kind of this big blue blob on the screen is the universe, right? You got to use your brain a little bit, right? You got to use your imagination here, right? And what we do is we break the universe into 2 different pieces, right? There's the system, that's the thing that we care about, and the surroundings, which is like the rest of the universe, right? Now thermodynamics, right, is like thermo, right? It's talking about heat energy. Dynamics, talking about mechanical energy, right? So this is really like, steam engines, right? How do we turn heat energy into sort of dynamic energy, right? Or mechanical energy, right? So we're very interested in this transfer of energy between the surroundings and the system, right? So one of the things that we'll have to do at the beginning of just about every problem is we have to define what our system is. What part of the universe are we interested in, right? then we want to say something like, is the system open or closed? Now, what does that mean, right? If a system is open, that means mass can come in and out of the system, right? Like if you think about your car, right? So I drove here to RIT today. My car engine has an air intake and an air exhaust, right? So air comes in and out of the system. But a closed system, for part of, we'll talk about internal combustion engines, but for part of the cycle of the internal combustion engine, there are two valves, intake and exhaust valves, that let air in and out of the piston. When they're both closed, there's nothing coming in or getting out of this piston cylinder assembly, right? So then it's a closed system. So a closed system means mass can't be transferred between the surroundings and the system, right? And then what we do is we say, if we're looking at a problem and how things change over time, we look at some initial time and we say, how much energy is in our system? And then we try to figure out how much energy is in our system after some amount of time has passed, right? So what's the energy change in the system? And then in this class, the types of energy transfer we're interested in are heat transfer and work. And the reason for this is, as mechanical engineers, oftentimes, like I talked about my automobile, right? The way that we get something to move is by burning something, right? So we're turning this heat energy from combusting fuel, in the case of my internal combustion engine, right? We're turning that into mechanical energy, that piston moving up and down, and then it's connected to different assemblies, and then, the wheels start to turn, right? So in thermodynamics, we're interested in how do we take heat and turn it into work? Or maybe more generally, how does the energy inside of our system change because heat is coming in and work is leaving? So in this class, we're going to talk a little bit more about work, right? Or work and power. So power just means work over time, right? The time derivative of work, right? So here, I'm not a huge fan of these big verbal definitions of things, right? So what this says, right, the first law of thermodynamics is that energy is conserved, right? So we can read all of this, but I won't read it to you because you can read it faster than I can read it to you, right? But here, the other thing too, all my notes, all these slides are posted online in the My Courses website, right? So I would encourage you to download them maybe before we start, right? You can print them out and write on them if you like to, right? But they're just there, right? And they'll be open to you during the exams as well, right? So this is the first law of thermodynamics for closed systems, right? And what this is telling us is we have this delta E on the left-hand side, right? And this is the change in energy inside the system, right? So, so here, if I had my tea mug, right, I wouldn't ever do this, but if I filled it with water and put it on the stove, right, then the water would get a higher temperature, right? So more energy would be stored in the mug, even though it's the same amount of water, but the water is at a higher temperature. So it then has more energy stored inside of it, right? So this is what this E term is. It's looking at the total energy in the system at some time, right? So here, E2 minus E1, this is the energy at the end of my process minus the energy at the beginning of my process. Right? Now, in this case, we're going to talk about, in thermodynamics class, usually we talk about energy going into the system by heat or coming out of the system by heat, right? So here, the heat in is positive, right? So if we're adding heat to the system, then Q is a positive number, right? And then from 1 to 2, this is the heat that goes into the system as we move from time 1 to time 2. Now, work's a little tricky, right? Because this is the net work done by the system on the surroundings, right? So we'll get into examples of this at the end of the class, but if you think about that piston cylinder assembly, when we spray some atomized fuel in there and the spark plug goes off, then what happens is the gas expands. So that's that gas pushing that cylinder down. So the gas is doing work on the piston, right? And again, as the subscript here from 1 to 2 tells us that we're moving from time 1 2 times 2. Right, so again, this is kind of the schematic. I like to draw these. I mean, it's kind of a bit basic, right? But in my system, I have some energy at time 1, and then I can add heat to it. Now, this is important because signs are going to be really important in this class, right? And units are going to be super important in this class. This is one of the reasons why when people hate this class, they hate it because there's so many units, right? Particularly if you're not a fan of the metric system yet. You will certainly be a fan of the metric system over the imperial system by the end of this class, because unit conversions are much easier to do when you're dividing by 1,000 versus by whatever conversion number you want to think of for the imperial system, right? So the thing for heat, when heat is positive, heat is going into the system, right? Heat in is positive. Right? And when heat is negative, that means that we're losing heat from the system, right? This is why, if you buy a coffee or a tea at Starbucks, right, you put that sleeve around it, right? Because that means you're losing less heat, right? So heat in is positive, heat out is negative, right? But work is the opposite, right? Where if work is done by the system on the surroundings, right, then that's positive. So work out is positive, and work in is negative. So if you were, so in the internal combustion engine, what happens when one of that cylinder is one of the pistons is being pushed down, there's another cylinder that's being pushed up, right? And that's the piston is pushing up on the gas to compress it, right? And that's work being done to the system, and that's work in. So work in is positive. Right? And when we know all that, if we put it into the equation, we'll be able to find how much energy is stored in the system at time 2. Right? So if E2 is bigger than E1, that means we had more energy in the system at the end of the process than at the beginning. Right? Conversely, if there's less energy in the system at time 2, then that means this would be a negative number. So we've lost energy in the system. We've depleted the system. Right? So again, you can sort of remember this by the words, which is my least favorite way to remember it. You can remember it by the equation, which I think is always very useful, or you can remember it by the little schematic that I've drawn here. Right? So this is telling us that heat in is positive and work out is also positive. Right? Now we remember that with this little mnemonic device, HIP to win. Heat in is positive, is HIP. Work in is negative, is win. So HIP to win tells us that heat in is positive and work in is negative. And it seems a little bit weird because they're both energies, right? Why is one positive and one negative, right? And it sort of goes back to looking at locomotives, right? Steam locomotives, right? So what you do in a steam locomotive, right, is you add heat energy, right? You burn coal, that coal boils water, right? And that steam, right? So as water boils, those molecules get forced further apart, and that steam wants to expand, right? And it expands over some kind of fan blade, and that sort of turns something, and then you've gone from heat energy into mechanical energy. So what these steam engines were doing, they were putting heat in, and they were getting work out. So both of those things are positive in this equation. I also just like the picture of that old locomotive, right? Right. So here, when we look at the energy in the system, right, what kind of energies are we talking about, right? So this equation you're actually already familiar with, although you probably never dealt with the heat term in a class like a first year physics or maybe even your high school physics, right? You were just thinking about energy and work, right? So there's different kinds of energy that we can think about. Right, so gravitational potential energy, right? So when I push my kids on the swing, right, maybe I pull them back so that they're at some elevation, and then I let them go, right? And gravity does the work for me here. So we get this transfer of energy from gravitational potential energy into kinetic energy, right? We can also think about spring energy, right? So this is a bow and arrow, right? So here, the limbs of the bow are like springs. So what the archer does is pulls back the string. The string is not supposed to be elastic. The string should be rigid. And and then the limbs bend, so you store the potential energy in the limbs, and then when you let it go, then that goes to kinetic energy in the arrow. Now, I use this example because I've been doing archery for the last little bit, right? And this is a total fluke, certainly not done on purpose, but this arrow is mine, right? Right into the back of this guy's arrow that I was shooting with. So probably only worked because they're both carbon arrows, right? So they're hollow, right? And mine's like a 5 mil and his like an 8 mil. So I don't think this would work with solid arrows, but just super lucky. I hit basically dead center on his arrow and it stuck in. It was wobbling all over the place. It looked super cool. So anyway, that was just one of the things I've been doing during quarantine is learning how to shoot bow and arrow. Right, just a recurve bow, so kind of like this guy here, not like a compound bow. Although now I'm excited, right? So you never know. Maybe I'll get into it. But there's more of a financial price to get into compound archery. So one of the kinds of energies that you probably never talked about in high school, right, or even in first year physics, is this this idea of internal energy, right? So we can sort of think about this, right? So these are some sort of metal pins, right? And you don't have to be like a rocket scientist to figure out which part of these pins has the most energy, right? Because as we heat this thing up, it's glowing, right? It's like, as we heat it up, those molecules, they start to vibrate, and they vibrate more and more and more and more and more, and that means that this part here has more energy than this part down here, or even this pin, even though it's the same material, because it has a different temperature, right? And as the temperature of that material changes, so too does the energy that's stored in it, right? So just like, I can store energy on a swing by elevating the mass, right? You can store energy in a material here by increasing the temperature, right? So in this class, we'll talk a lot about this thermal or internal energy. Right, so we'll have to figure out how much energy does steam have when it's at a particular temperature or a particular pressure. Right? So the total energy, E, that was on the left-hand side of our equation, is a sum of all this stuff. It's the kinetic energy plus the potential energy plus the spring energy plus this new thing, this internal energy, right, which we call U. Right? This is the new part of our equation. Right? So this is total energy, right? This is kinetic energy, right? So it's made up of kinetic energy plus potential energy. We're used to these things, plus spring energy. But in the problems we're interested in this class, right? So things like how does an internal combustion engine work, right? Or how does a nuclear power plant work? Or how does a natural gas power plant work? Usually the kind of energy that we're going to be interested in is this new kind of energy, this internal energy, which is related to the temperature and the pressure of whatever material, whatever mass we're talking about. Right, so you do kind of already know this, right? So we can write the left-hand side of this equation out. Instead of just as delta E in our equation, right, we can say that it's, delta kinetic energy plus delta potential energy plus delta spring energy plus this delta internal energy, right? So we can expand out the left-hand side of this equation, right? And now our first law looks like this, right? It's the change in the kinetic energy plus the change in the potential energy plus the change in the spring energy plus the change in the internal energy is now equal to the heat that comes in minus the work that goes out. So this is the same equation as before, but we're expanding the terms. Because what happens in these sort of thermal fluid problems, right? So when we're started to look at like heat transfer, thermodynamics, fluid mechanics, we have good equations, but we usually don't know all the inputs. So we break the terms apart like this because in a lot of the problems that we talk about, kinetic energy, potential energy, spring energy, they're not going to be that important, right? So we'll assume that delta E often is just delta U, right? And we'll talk about how to fix that later, right? So you know this already, right, from your maybe mechanics class, right, or maybe even high school physics, right? But they didn't tell you all the assumptions that you're making. Anytime you write down an equation, this is one of the things we really want to hammer through in this class, is every time you write down an equation, there are assumptions that are implied by that equation, right? So here, if we write down this version of this equation, In engineering mechanics, you probably said, oh, that internal energy, it doesn't matter. We can assume that the change in internal energy when you're on a swing set is about zero. Your temperature didn't change that much as you were swinging on the swing, right? You also didn't have too much heat that was entering or leaving your body as you're swinging on the swing, right? And then what you got was the change in the kinetic energy, the change in the potential energy, and the change in the spring energy was equal to the mechanical work, right? And that's something that you may have seen before, right? But they didn't necessarily tell you that you were making these assumptions, right? And again, this is one of the things, just like if you ever, when you go out on co-op, it's one of the things that's going to be really important that you leave good documentation behind, because these co-op positions are just transient. You're only there for, a short amount of time, right? So you want to leave good notes so that whoever comes after you can pick up where you left off, right? Your first introduction to this will probably be when you come in as a co-op and you get the last co-op's notes and you realize that half the stuff that you want to know is not there, right? This is kind of like commenting in programming, right? Which is something that maybe I should be better at for sure, right? But you want to have good notation, right? And that's what tracking your assumptions does, right? So in thermodynamics, unlike solid mechanics, we're going to be really interested in internal energy and heat transfer, right? It's thermodynamics, right? So we're interested in temperatures. We're interested in heat transfer, right? Because that's one of the two main kinds of energy transfer that we're looking at, right? So we can't just cross out Q and we can't just cross out delta U. We're going to, for now, leave this whole equation, right? This only works for closed systems. As we get into open systems, when mass can move freely in and out of a system, then we'll have some more terms to deal with. But for now, we'll leave this equation like this, right? And we won't beforehand make any simplifying assumptions. When you get into a particular problem, maybe you'll say, oh, there is no kinetic energy change, right? Or there is no potential energy change. So you might cross out some terms for each individual problem, but at the base level, we're going to leave the equation like this. Right? So that's kind of where we get into work, right? But then we talked a little bit about power being important too, right? So power is work divided by time, right? So, when you look up a particular automobile engine, right, you might be interested in what's the horsepower of that engine, right? So that's, horsepower is kind of one of those imperial units that doesn't make a lot of sense, but it's talking about how much work does it put out per unit time, right? Now, typically in this class, when we see a dot above a letter, this is shorthand for taking the derivative with respect to time, right? So this is like dw by dt is the same thing as w dot, right? It's the rate of change with respect to time, right? So that's not an uncommon bit of notation in mechanical engineering. So we know that power is some work divided by some time, right? So if if the work was constant to get this rate, we could just take work and divide it by delta t, right? So if the rate of work was constant, we could do this, right? But the rate of work's not always constant, right? But at least, as a first approximation, we could do this, right? So we can look at the units now, right? So if I say like a process takes, it produces 1 joule of work in 2 seconds, what's the average power output, right? Now I do all this, I got to track my units in my calculation here, right? W dot 1 joule divided by 2 seconds, right, is half a joule per second, but a joule per second is the same thing as a watt, right? So watts are joules per second, right? So now we want to talk about what happens here. So certainly not advocating that you do this, right? But maybe you got a potato gun, right? So it's a PVC pipe, right, with a potato as a plunger, right? Now you have air that's in that thing that's at some high pressure, right? Now in this case, right, what's happening is we pull this pin, right, maybe like a firing pin, right? And then what happens is, right, this air, it's under pressure. It wants to push out, right? Because this pressure is force times area, and if the rest of this is rigid, right, then it's going to be pushing force on this piston face, or a potato, in the potato gun case, and that's going to cause this piston to move this way, right? That air is going to be doing work on that piston face, right? And it's going to move, right? So when we pull this pin, then the piston's going to move, right? The air pressure is going to push the piston out, right? So now if I want to find the work or the power, what I can do is if this pressure is constant, I can find the force on the piston by taking the pressure times the area. If I was using sensible units like the metric system, then I would have pressure as pascals, which is newtons per meter squared, right? Force per unit area, multiplied by an area, and I would get newtons, right? If I was using the imperial system, sometimes called the US customary system, right? Then I would be taking pressure, maybe in a unit like pounds per square inch, or PSI, right? So that's pounds force per square inch multiplied by inches squared, right? And I get pounds force, right? So that's good. I'm getting force, right? So then, because in this case, this pressure is going to be changing as the piston is moving, I need the force as a function of x, right? So I would take, to find the work, I would have to integrate the force over the length, right? But just for unit's sake, right? So let's say you don't trust me with this equation, right? Let's at least check the units. This is kind of like one of the things we'll learn in this class. Checking the units is a bit like cheating, right? Because you can always check the units, right? It's never going to tell you if you're right, but it could tell you if you're wrong, right? So if work, right, which is a kind of energy, if I got Newton meters squared here for work, then I know that's wrong, because joules, right, which is energy, is newtons times meters, right? Or maybe if it's in imperial, maybe it's some force times distance, so maybe it's inch pounds, right? So I can check this. My force is going to be in newtons or pounds force. My distance term could be in meters or inches, and I'm going to get a force times the distance, right? So that looks good so far for work. But, and if you want to look at the, I think the full lecture that's posted online, I go through a derivation of this equation, but I wanted to try to hit the time here, so I got rid of the derivation here. But another way to write this equation down, right, this force times dx, another way to write this down is take the integral of pressure times dV, right, where here our big V is volume, right? So this is, we're integrating the pressure over the change in volume. Right, so now, again, I haven't shown you the derivation, although you can see it in the online video if you want. You might not believe me, right? So let's at least check the units, right? Because if the units are wrong, then you know for sure that I'm wrong, right? But here, right, we can see we want joules again, right? So if my pressure was in newtons per meter squared and my volume was in meters cubed, then what I would get is Newton meters, which again is joules. So this equation, it is correct, and we'll be using it a lot, but one of the ways you can check that it's correct is by looking through the unit, right? If we were talking about imperial units, right, then again, our pressure is going to be something like PSI. Volume could be in inches cubed, if I want to save myself the headache of if I put this in cubic feet, right? Then here, right, again, inches squared, right, cancels out two of these, and I'm left with inch pounds, which is a unit of energy because it's force times distance, right? Or distance times force, same thing. Right? So this is a very important relationship, and we'll be using it a lot in this class because as we talk about these, things like piston cylinder assemblies and how much work is being done, we'll want to know what the pressure-volume relationship is, right? So we'll often be talking about what we call polytropic processes. And a polytropic process is a process where we know the relationship between its pressure times volume to some exponent is equal to a constant. In next class, we'll learn about how to deal with that to solve for work. Right? So pressure can be a function of volume, and if we know that, then we can analyze arbitrary cross-sectional areas if we know what the pressure is as a function of volume, right? So I can put this in, if I write down pressure as a function of volume, I can put this into this equation and I can get a value for work, which is good, right? Because my big equation for the first law is delta E is equal to Q minus W, right? So this class is really about how do we find W, right? So the most important way we're going to find W for the first third of this class is going to be we're going to take the integral of P dV. Right? So if we have these polytropic processes where P times V to the N is a constant, then P will be C divided by V to the power of N. Right? And then I could plug that back into here and do a little bit of calculus to find the amount of work in the system. Right? So oftentimes we'll see in a problem, it'll tell us, PV to the N is constant, but they'll tell us N will be something like 1 or 1.3 or 2, right? So we'll get that relationship as given information in a problem. So we're going to go through this example reasonably quickly, but if you'd like to see it, so in addition to the full lectures that are online, I also did something called thermo shorts. So for each lecture, there's kind of like a 5 to 10 minute overview of what the lecture is supposed to be. I think I was normally in that 5 to 10 minutes. Maybe a couple times I spilled over. But those thermo shorts lectures, which are also on my YouTube channel and linked to from the My Courses page, you'll be able to see how we did this, or you can go through the long version of the lecture that's posted and see how to do this, right? So here's the problem statement, right? We have a gas contained in a piston cylinder assembly, and it expands at a constant pressure of 4 bars from some initial volume to some final volume. We're asked to calculate the work. Now, because the pressure stays constant, there must be something that's feeding this system to keep that pressure constant. Because normally, as a system expands like this, if the gas in there is some finite volume or finite mass, then the pressure will decrease, right? But in this case, the pressure is constant. And that keeps the math relatively easy for us. So if we go through kind of our stock process for how to do problems, then what we do is we take our known information, right? So we got to look through the problem, right? So the first thing here is that it's a constant pressure process, right? So the pressure stays the same all the time, which is good. Anytime something says constant, there's a little voice in my head that's cheering, right? Because it means that I don't have to do a lot of calculus, right? It means that the calculus will be pretty straightforward here because the pressure is constant. Right, so I know that the pressure is constant, but even more than that, I know what the value of the pressure is. The pressure is 4 bars. Now, my advice to you, every time you're writing down known information, is to write the pressure down in kilopascals if it's a metric problem. Because the units will just work out well if you integrate PDV and your pressure is in kilopascals and your volume is in meters cubed, you'll get kilojoules. Right, so this is in bar, but we'll see that we have to convert that later on in the problem. We know we go from a volume of 0.15 meters cubed to a final volume of 0.36 meters cubed. And they ask us to find the work, right? Work equals force times distance, right? Or pressure times change in volume, right? In that distance, they want in kilojoules. So not only do they want the work, but they tell us what units they want the work in. Right, so here, one of the things that we always want to do is draw a schematic. Right, so our schematic might look like this. Right, it's this piston cylinder assembly. We have some fluid in here that's at some constant pressure. And because we're moving from a smaller volume to a larger volume, our system is expanding. Anytime a system is expanding, it means that the fluid is doing work on the surroundings. So this is work out. We're expecting this work value to be positive because the gas is pushing out on the universe. Now we know that the pressure here is constant, so one of the things that we like to do is draw PV diagrams, or pressure versus volume diagrams. Now the cool thing about this, right, is because the work we're trying to find is the integral of PdV, right? Now, if you remember from calculus class, that means it's the area under this curve, right, is the integral of PdV. So in this case, it's nice because the pressure is constant, right? So you could just do this geometrically, but we'll go through the equation, right? But you could just take the area under this curve, and because it's a rectangle, we could get to a pretty good answer just from drawing this diagram, right? That's one of the reasons that drawing diagrams is always a good idea. Right, so we're going to write down our assumptions. We assume that the pressure is constant. We're going to neglect any kind of friction in the system. We're also going to assume that the mass is constant. They didn't tell us that, but we're going to assume that none of the mass in the system is leaking out to the surroundings. Right, so now we want to find the work, right? So we need an engineering model, right? What's your equation, right? Or what are your different equations? Here we just want work. So there's one equation, and that's work is the integral of PdV. Right? I apologize, I'm a little bit over, but I think we'll be done in a couple of minutes here. Right? So we know that the units here make sense. So when I write down an equation, I always want to think about the units. I want work, right, in kilojoules. Right? So if my pressure was in newtons per meter squared and I multiplied by meters cubed, right, then I get Newton meters, which is joules, which is at least in the same family as kilojoules. 1 kilojoule is 1,000 joules, right? So here again, I sort of have reasonable confidence in this equation because the units look like it would be correct, right? So, so now I'm actually going to start doing the work. I'm always going to encourage you to do as much of the work symbolically as you can before you put numbers in, right? Because that will help me understand what you're doing when I'm grading you. But more importantly, you know, again, when you're in the real world and you do a project and you come back to that project 6 months later and you go look through the work that you did 6 months ago, you're not just going to remember what happened, right? So the more you do this symbolically, the better it is. It also means when you have it symbolically, then as you're designing something and you change a given parameter, you already have the governing equation, you just put different numbers in. So carry the symbols throughout the process as long as you can. Right? So because we know that the pressure is constant, we can bring that out of the integral. Right? Now, this is good. My favorite calculus is always when the answer is 0. But this is my second favorite calculus when something is constant, because now I just have the integral of dV from V1 to V2, right? Which is just going to be delta V. Right? So here, my pressure is constant. I got to remember that it's V final minus V initial, right? In this case, the system is expanding, so the final volume is larger than the initial volume, right? And now I put units in, or I start to put my numbers in, right? So this is like my symbolic solution, right? But I want an actual number, right? So now I'm going to put numbers in. But when I put numbers in, I got to put units in as well, and we'll see why here. Right? Because here I have, remember my delta V term, these are both in cubic meters, right? But my pressure is in bar. So if I just put these numbers into my calculator, it would look like what was that, 0.84? But it'd be 0.84 bar meters cubed, which doesn't really make any sense because what we actually want is work in kilojoules. It's not like that other answer is wrong. It's just in a unit that nobody would ever talk about, right? You can't go to Home Depot and get a pump, you know, that outputs some kind of work in bar meters cubed, right? So instead, we want kilojoules here. So to get to kilojoules, we have to convert the pressure term. Now again, my advice is always going to be in metric, always convert pressure to kilopascals right at the beginning of a problem. So a bar is 100 kilopascals. It's right around atmospheric pressure. Atmospheric pressure is about 101.3 kilopascals. But the metric system doesn't really like that because the metric system likes nice round numbers. So we made up another unit called bar. So bar is 100 kilopascals, right? Or 10 to the 5 pascals. Right? So we can put that in here. Right here, I put this in my units, right? So this is 4 bar, but each bar is 10 to the 5 newtons per meter squared. Right here, I'm adding an extra step, and you'll see why I like to do kilopascals too, right? Because here, right, so I cancel out my bars, right? And then meters cubed divided by meter squared just leaves me with meters, right? Which is nice because over here I got newtons on top, right? So now I take 10 to the 5, multiply by 0.21, and I get 84,000 Newton meters, right? I know that Newton meters are joules, right? And this is maybe I'm going a little overboard with the unit conversions here. Some of these you can just do in your head, right? But I want to show you how I do this mathematically, right? I take 84 Newton meters, right? But I know that 1 joule is equal to 1 Newton meter, right? So now my Newton meters cancel out, and I get 84,000 joules, right? But I know then that 1 kilojoule on top is 1,000 joules, so now I can cancel out the joules, and I get 84 kilojoules. Now, my life would have been a little bit easier if I would have gone back here and automatically put this in, instead of converting this to 100,000 pascals, if I just converted this to 100 kilopascals, then I would have just had kilopascals times, or I would have ultimately had kilonewtons times meters, which would be kilonewton meters, which would be kilojoules. So if you put your pressure in kilopascals, your life will end up being a little bit easier. So then the last part of our process here, and maybe you're not as familiar with doing this, is we want to test. We want to think back and say, like, does our answer make sense? A bit of a sense check here. So one thing we can always do, even if we don't have any kind of intuition about what the order of magnitude of the number should be, we can always check the units, right? So we were asked for work in terms of kilojoules, and we got an answer in kilojoules. It doesn't mean we're right, but we can't prove that we're wrong, right? If we still had an answer in bar meters cubed, then we'd know we didn't really answer the question, right? So just because your units are right doesn't mean that you're right, but if your units are wrong, it means that you're wrong, right? So having the right units increases your confidence, but it doesn't necessarily make you right, right? So we got the right units, right? The other thing that we can do is we can check the sign. So we know that the system is expanding, that the gas is pushing out on the piston, which means that the system, that's the gas, that's the part of the universe we're interested in, is doing work. It's pushing that piston out. So we know from hip to win that work in is negative, but this would be work out of the system, so this should be a positive number, right? And we did get a positive number, which again doesn't mean that we're right, but it means that we can't prove that we're wrong. And that's a pretty good thing, right? So we can't prove that we're wrong. We tested these things, and we see that, that they worked out, right? So I don't know if my answer is right, but I can't prove that it's wrong, and that's something. Right, so that is the end of the class today. Next class, we'll do a problem where the pressure varies with volume, so that you can see how to do something like that, which will be more in tune, I think, with what the homework problems are. Does anybody have any questions before we sign off for the day? All right, excellent. I will see you all tomorrow at the same time. Thanks, everyone.
Thank you. Thank you. Have a great day.
You too. Bye-bye.
Thank you, Professor.